Welcome to lecture number 9 for new N302. Last lecture we talked about the macroscopic cross-section. We related that to our microscopic cross-section, something that was covered in a lecture prior to that. And just as a reminder, each of these cross-sections, they have units, they have different units. Our microscopic cross-section has units of area. It's typically a really small number, and so we're going to employ the unit of barns, which is 10 to the minus 24 centimeters squared. For the macroscopic cross-section is typically given in units of 1 over centimeter, so 1 length to the negative 1. And in each of these cases, they are related to the probability. And what they do is they convert numbers of possible reactions to numbers of actual reactions. And so what are the things that dictate possible reactions? Well, it's mainly just the amount of neutrons that we have in that spot, in that volume, and the amount of nuclei we have in that. How many atoms do we have in that same volume? So those two numbers represent the possible reactions that I could have. And the cross-section is the parameter that helps us convert the possible reactions and possible interactions to the actual reactions or interactions. And so many times you'll hear people, when they discuss cross-section, they almost hand in hand are going to talk about probabilities. And it's because of that very reason. We're taking the possible interactions / reactions and converting them via the cross-section to the actual reactions that we have. And so we can relate one in terms of the other, and they're both properties of the isotope. So if we know that we have uranium-235, we look up the cross-section. And if we know the speed of the neutron, we know the energy of the neutron, then we have one number for that cross-section. So today we'll develop an expression that sort of formalizes that relationship between the probability of something happening and the cross-section. And we're going to extend that to look at how many neutrons make it past a certain number of molecules or certain thickness of the target. This is important. These are important metrics to look at when we talk about shielding and trying to answer that question: how thick of a layer do I need to capture all the incoming radiation? And then we will look at a slightly more complicated scenario, but one that is at least one step closer from this super idealized scenario that we've been discussing, 1D, one neutron beam. Once the neutrons interact with some nucleus along the way, then we forget about them. In these expressions we're going to develop. And we know that's not true, right? A neutron, as it's going to go through some elastic scattering, for instance, then it's going to have some angle that it scatters at, and then eventually is going to hit another nucleus. So in this analysis that we do at the beginning, it's going to be simplified, and then we're going to make it just ever so slightly more complicated to look at homogeneous mixtures. And so very rarely is the target going to be comprised of a single isotope. It's going to be multiple isotopes, multiple elements. We'll do an example with stainless steel, for example. So stainless steel isn't something you look up in the periodic table. It's going to be comprised of a certain number of elements. And every naturally occurring element is also going to be comprised of certain percentages of different isotopes. This is the reason why carbon does not have naturally occurring carbon does not have an atomic mass of 12. Now carbon-12 does, that isotope does, that's how we defined AMU. But naturally occurring carbon is going to be comprised of mostly carbon-12 but a little carbon-13. And so when we look at these mixtures with multiple isotopes, multiple elements, we want to be able to, we can look up data for the cross-section for each of those isotopes, but we really want to know what is the overall cross-section, whether it's absorption cross-section, scattering cross-section, fission cross-section. We want to know what it is for this whole mixture, this homogeneous mixture. And we're going to restrict ourselves to homogeneous mixtures. In many cases in the real world, even in a fuel pellet, it's not, especially over time, it's not necessarily a homogeneous mixture. There's going to be layers of different isotopes. but for the intents and purposes of what we do in this course, everything's going to be a homogeneous mixture. And we'll look at those in terms of either fractional abundance. So in the case of naturally occurring carbon, you've got 99 point something percent of C12 and the rest is C13. Or we might look at it in terms of mass fractions or weight fractions. That's what we're going to employ when we start talking about enrichment ratio and that sort of thing, enrichment percentage, sorry. So we're going to start looking at this target that is no longer a thin target, but we want to use the analysis that we did for a thin target to help us understand and characterize what's happening in this thick target. And so we take this target of thickness L, and we're going to take a thin slice of that somewhere in the middle, this delta X here. And if I look at the neutron flux, that's this phi X here, and then I have some distance later that delta X is going to have a different neutron flux, and so the difference between those two, and if I multiply that by the cross-sectional area, the target area, then this represents the number of neutrons that interacted with the target between location X and between location X and location X plus delta X. That's what this expression would tell me. If I know the neutrons coming at this location and it's a different number coming downstream of that, then I know the number of neutrons. The difference between those two is the neutrons that happen to interact between the two locations. And so I can express this. I can express this also in terms of my cross section. Right. So I'll take this this expression here, phi x minus delta x, and multiply that by area. That is also going to equal my macroscopic cross-section, this is what we did last time, times the thickness, in this case not the thickness of the target, but the thickness of that little slice that we're analyzing, times phi of x times the cross-sectional area. Now these areas obviously cancel out, and we're left with the following. Divide the delta x over, that should be the plus delta x in each of these, sorry. Divided by delta x is going to equal our macroscopic cross-section times the flux. So as I take this at the limit as x goes to 0, so as delta x goes to 0, as delta x gets small, then what we have on the left-hand side is basically the derivative of phi, the ddx. Now it's the negative ddx of that, just because I've got the x plus delta x as a second term, and so if I reverse those, that is my ddx. Then I've got d dx of phi of x on the left-hand side, and then I've still got we'll put the minus over here. So I got the derivative equals this constant times the function. I can separate and integrate, and I've got d phi over phi equals minus sigma times dx. I'll separate and integrate. In this case, I'll go from phi naught, that is, I'll call that whatever's coming in at the first surface, over to phi, and then from here we'll call this from 0 to x. And so what I have then is the natural log on this side. So the natural log of phi evaluated between phi naught and phi, that's going to equal the negative cross-section multiplied by x. And I'm evaluating from x to 0, but I take the exponential both sides, and I get that phi of x is going to be phi naught times the exponential of negative sigma times x. And so this here and this is what you see in the caption of this figure that I copied from the textbook. This is going to exponentially decrease. And it's never going to go to zero truly, but it's going to exponentially decrease from location 0 from a value of phi naught at x equals 0 to a value of phi at some other location, whatever that x happens to be. So let's go to our first example. In this case, we are going to consider a one-speed neutron flux targeting a thick slab, and we want to determine the distance into the slab where the flux has been reduced to exactly 1/2 of its incoming value. So the flux at location x, in this case x half, is going to equal 0.5 of phi naught. So let's do that first part. We want to express it in terms of our macroscopic cross-section. The second part is we're going to talk about this E-folding distance. It's going to be real similar type of analysis there, but let's do this first part. So we have phi of, we're going to call this value x 1/2, and that's going to equal phi naught over 2, and the expression we just developed a minute ago is phi naught times exponential of negative sigma x, and so my phi naughts cancel out. And I want to solve this. In fact, this here should be x half as well. I want to solve this for x half, and so I take the natural log of 1/2 equals, and I take the natural log of the exponent, and I get negative sigma x 1/2. This negative 1/2, or this 1/2 is 2 to the minus 1, and so that negative, I can cancel that out so that I can solve for this x 1/2. This is going to equal the natural log of 2 divided by my macroscopic cross-section. Okay, now we want to find this E-folding distance where the neutron beam has been attenuated. Attenuated means decreased by a factor of 0.368, which is equal to e to the minus 1. And so we'll leave that in here. We'll say that phi of xe, that's going to equal e to the minus 1 times phi naught. And that also equals our function we just developed, phi naught times the exponential of sigma times x. Again, our phi naughts cancel out. And we're going to take the natural log of both sides. We're left with negative 1 equals negative sigma x. In this case, this is xe. So xe equals 1 over. And so if I know my macroscopic cross-section, you can see that both of these are functions of my macroscopic cross-section. And it really is going to tell us a lot of things that we need to know in terms of predicting this or predicting that. And in this case, what this top equation here represents is the thickness of the material that I need in order for my beam, my neutron flux, to be decreased by a factor of 2. In this case, I want to decrease it by a factor of 70, almost 70%, 64% or so. And so this then, if I know my macroscopic cross-section, I just invert that, and now I've got units of meters, and that's how thick the material needs to be for that E-folding distance. So let's go back to the lectures here and try to relate this back to probabilities. So what are we doing? What are we doing with probabilities? Well, if we look at that expression for phi x and divide that by phi naught, this represents the probability This represents the probability of a neutron reaching that location x without any interactions. In other words, it's still there. And it's not that the neutrons disappear. It's not that we don't have to account for them in reality. But in this simplified analysis, that's kind of what we're doing. We're saying for the neutron to reach location X, for the phi of X to still be counting that neutron, it has to not have interacted with anything up until that point of X. And so this then is the probability of a neutron reaching X, whatever location that is, without any interactions. And so if I take this expression and I look at my exponential function that I just derived, then that same thing, phi of x over phi naught, that is just exponential of minus sigma x. That's my macroscopic cross-section. And that also is my probability of a neutron reaching some location x without any interactions. And so if I want to express kind of the inverse of that, or the alternative of that, is the probability of a neutron having some interaction, at least one interaction up to that point x. And that will be just 1 minus all that. So this then is the probability of experiencing at least one interaction. And I say at least one because, again, in reality, that neutron's going to have, there's a high chance, depending on how thick the target is, that the neutron experiences more than one interaction, especially when we're talking about scattering events, of at least one interaction up to that value x. So with that, let's go to another couple examples and express these probabilities in terms of the cross-sectional. So in example 9.2, we want to know the average distance that a neutron travels before having its first interaction. So we know the probability up to a certain point, but we want to know for a given neutron, this neutron is going to make it this far, this neutron is going to make it a different distance, on a case-by-case basis. But if we look at the statistical average of those, on average, how far does a neutron got before it starts to interact? And this again helps us answer that question. Well, how thick does the target need to be? How thick does this layer need to be in order to attenuate, on average, these neutrons down to a level where maybe I'm not as concerned about them? Or the same concept applies to gamma radiation, for instance, or alpha radiation. And so the average we're going to express in terms of these brackets here. So I want to know what the average x is. In order to find the average x, I've got to, let me scoot this down a little bit. In order to find the average x, I need to integrate over the probabilities. So I'm going to have a probability of x up here, and I'm going to integrate from 0 to L of that probability of x down here. Go 0 to L dx. And in order to find the average, I just need to add, or not add, but to include an x in that numerator. And so this then is the formal definition of the average of some distribution, this probability function from 0 to L. And so I substitute the expressions for probability that we just developed, and that will be 0 to L x times exponential of minus x. 0 to L of x, just exponential. So the numerator, or the denominator down here, is an easy one. The numerator is a little bit more challenging. We're not going to go through it here, basically integration by parts. But we can do this, and then we find an expression in the numerator is going to be negative plus 1 exponential sigma x. And we'll evaluate that from 0 to L, and then we'll do the same thing in the bottom. This one's an easy one. We'll evaluate that from 0 to L. And what you find is that, again, related to my cross-sectional, my macroscopic cross-section, so this is then my expression for the average distance that a neutron has before its first interaction. And you notice that as L goes to infinity, then I'm left with, it's worth noting here. So as the thickness of that layer, or the target, goes to infinity, then this is going to go to 1 over my cross-section. And so the target is thin, quote unquote thin, if the actual thickness is much less than this one. We'll call this x of infinity. And so target is thin when the true thickness is much smaller than what we calculate here. And the target is thick when L is much larger than that. And this parameter here is known as the mean free path. The average distance that a neutron can make it before interacting with anything. That is my mean free path. So if we look at the next example, example 9.3, we have two slabs placed together, slab 1 and slab 2. We have thicknesses L1 and L2, and then cross sections. It should be sigma 2. And we want to know the probability of a neutron having its first interaction in that thickness here. And in part B, we want to know the probability of a neutron having its first interaction all the way from 0 to the end. And then in part C, we want to find out how many neutrons make it out of both slabs without any interactions. Now, if you're paying attention, then you'll see that whatever the probability is for part A, and then you say, well, I've got this much left over, and then I have an additional probability of making it through the next layer. Then I've got the rest of them all have to go through without any interaction. So if I know part A probability and know part B probability, then I recognize the fact that every neutron is either going to have a first interaction in L1, have its first interaction in L2, or escape without any interaction. 100% of the neutrons have to fit one of those three categories. So once I find the probability of A and probability of B, then I just say 1 minus each of those, then that's going to be my probability for part C. So for part A, this is easy. We just look at my probability. Making it through without an interaction would be 1 minus the exponential of sigma 1, so the cross-section of layer 1, times the thickness of layer 1. That represents how many neutrons make it through, or how many neutrons have their first interaction in L1. And in part B, what I'm going to do is I'm going to take whatever's left over, which will be exponential. Since this was 1 minus the exponential, this will just be exponential of that same quantity from layer 1. That's what I'm starting with at layer 2. That's how many neutrons are left without having interacted with anything at the interface between 1 and 2. And then I'll multiply that by the probability, the local probability, if you will, of layer 2. which will look just like it did for layer 1. And for part C, then, my probability for part C is just going to be 1 minus the probability of A and the probability of B together. And that's going to be my total probability. Every neutron, again, has to be one of those 3. And I know that those have to sum to be 1. And so I do the math there, and I get the probability for this one is just going to be the products of exponential of sigma 1 L1 and the exponential of sigma 2 times L2. Okay, let's go back to our lecture. We want to now look at a volume flux. And here's our definition for volume flux right here. For a 1D system, this is going to simplify. Then dV is just going to be dA times, or x times, sorry, A times dx. My cross-sectional area times some infinitesimal thickness of dx. And so I'm going to now look at my volume averaged in 1D and do this integration. Instead of a volume integration, I'm just going to do a 1D analysis. So this will be phi x times A times dx. That's my numerator. My denominator is just going to be the volume integral. In that case, it's just going to be A times L, whatever the total thickness is. And so I've got my areas that are going to cancel out. And so this just equals 1 over L times 0 to L of the expression for phi of x, which again is phi naught times exponential of negative sigma times x dx. And so this here, just to make sure we understand, this is going to be the thickness, the overall thickness of the slab. And that's why I'm integrating from 0 to L in the x direction. So as I integrate that, then this volume integral of flux is just going to be phi over L, phi naught over L, times the, we've already done this integral once, L. Oh, we forgot a sigma here. That's right. And so the total interactions then is going to be the, if I go back to my definition of reaction rate, no, this isn't a rate actually, this is total interactions. That capital R is going to equal phi naught times A times 1 minus exponential of sigma L. You'll see that these quantities here, I got sigma naught, and then I've got this. These two together are just going to be that volume integral of the flux times L times my cross-section. And so I can express my reaction rate with the equation that we have here, or I could express it just in terms of that volume averaged flux times A times L times sigma. But this is just going to be my volume average flux times the volume multiplied by sigma, because this A times L is volume. So for certain types of reactions then, whether it's absorption or scattering or fission, each of these have their own cross sections. And so I can express this reaction rate, or this reaction, the total number of reactions, in terms of Rj, where J now represents the different types of cross sections that I have. This will just be the ratio of the cross section that I'm interested in over the total cross section, multiplied by the total number of reactions. And so I use this expression here times the volume integral of phi, V times J, and this then equals phi naught times V, gotta have the L in there, times now my ratio of the cross-section that I'm interested in over the total cross-section, 1 minus exponential minus L. And so I know the thickness of the material. This here is just A. I know the thickness of the material. That's L. I know the cross-section, that's A, and presumably I know the cross-sections of absorption, or the cross-section of the fission, or whatever it is I'm interested in, that sigma J. I know the total cross-section, nuclear cross-section, and so I can then predict, based on what flux I have coming in to this target at x equals 0, I can predict how many through the whole thickness are going to react in terms of fission, or in terms of absorption, or in terms of scattering. So I can do this for each and every component that I want to, each and every type of cross-section that I want to. And now if we want to apply this to homogeneous mixtures, we just need to recall the definition for the macroscopic cross-section in terms of my microscopic cross-section is just sigma equals, capital sigma equals lowercase sigma times n, where this, again, as a reminder, this is my atom density in the target. So n equals rho times Avogadro's number divided by my molar mass. And so for mixtures, that expression there is for a homogeneous material of one isotope. So for mixtures, then this becomes the sigma J, where this is the J-type interaction, whether that's fission or whether that's absorption, or whatever type of interaction we're looking at. This here, this is my microscopic cross-section. For the J-type interaction. For isotope I. That's what this superscript I means. And then, of course, my Ni is going to be the number, the atom density for isotope I. So that's a little bit on the nomenclature there. And if we know the atom fraction of the homogeneous mixture, then we can quite simply just express this in terms of that fraction F. So I have my macroscopic cross-section of J-type interaction. That's going to be equal to this atom fraction. And I'm going to use a subscript n there, as the textbook does, meaning that it's a number. I'm looking at numbers of atoms, for example. But that's going to be different for each isotope. So that superscript I, again, refers to isotope. And I multiply that by the total number density of atoms in my mixture. That's n. So notice there's no longer, because now I have this here, I don't have to worry about n superscript I. I don't need to know the atom density of each isotope. I just need to know the total atom density of my mixture, and I multiply that by the atom fraction of whatever isotope I happen to be looking at. So that's replacing Ni, and then of course I still have my sigma of the J-type interaction and of isotope I. And so this nomenclature here, this is going to be my atom density, or no, my atom fraction, I'm sorry, for isotope I. So in a more general sense, what we're going to do is just create a summation of all these. So I have X number of isotopes that comprise my mixture is comprised of. Then I'm going to have this type of term. I'm going to have X number of terms. And so this can be a little confusing because the symbol that we use for summing up multiple terms is indeed capital sigma, the same as our macroscopic cross-section. So I'll try to, maybe I'll do it a different color just to make sure we differentiate that. But in general, then, my macroscopic cross-section of type J, and we'll do M as a superscript here, this just means mixture. Then this is going to equal, a little bit bigger too, so that's the summation of Ni sigma Ji. So going back to this definition up here. If I have how many of our isotopes that make up this mixture, then I'm going to have that same number of N times sigma products. But I can use the new definition for, not the new definition, but the definition we just found here, and this will be over J. Oh, this will be over I, I'm sorry. I have I isotopes. Then this is just going to be F N of the mixture times F, the atom fraction of the isotope, multiplied by that microscopic cross-section. And you notice this here can be taken out of the summation since it's not different for each isotope. So then this is going to equal the number density of the mixture multiplied by that summation over the different isotopes that the mixture is comprised of, multiplied by, or I'm summing the product of the atom fraction of each isotope and the microscopic cross-section of each isotope. So this is one way to look at it. If we have the numbers for the atom fractions, this is the most straightforward way to look at it, to analyze it. But if I have, for instance, the mass fraction, also known as the weight fraction, and this is the symbol right here that a lot of times you'll see tied to that call-out. If we're talking about mass fraction or weight fraction, it's the same number. You'll see this here as a call-out for that. And if we're given that, we're going to use this F sub W so to denote the weight instead of some number of atoms, for instance. Then we can express this for a given isotope I is going to be the density of that isotope divided by the density of the mixture. And we'll make use of the fact that the density of isotope I is going to be proportional to the atomic mass of that isotope multiplied by its number fraction, by its atom fraction of molecule, or atom fraction. And the same thing can be said about just density of the mixture, that it's going to be proportional to the molar mass of the mixture. And it's the same proportionality in this case, and so we can just say that this F, the weight fraction for a given isotope, is going to be equal to the ratio of the mass, or the molar mass of that isotope to the molar mass of the mixture multiplied by the number fraction, the atom fraction. And so I'm going to solve this for my atom fraction, and I'm going to substitute that back in. That's going to be the molar mass of the mixture divided by the molar mass of the isotope multiplied by the weight fraction, by the mass fraction. And so I'm going to take this and substitute that into the expression we developed just a minute ago to come up with a similar expression in the event that I'm given the mass fraction instead of the atom fraction. And it's going to be a more common scenario to be given the mass fraction, and that's why we're doing this. And so I eventually am looking for the cross section of the mixture, this cross section type J for the mixture, and that's going to be equal to the number density of that mixture multiplied by the sum across I of my different isotopes. And I'll just substitute this in there. So I've got M over Mi times the mass fraction, and then I've got my microscopic cross-section there. But we can simplify this a little bit more and make use of this here and this here. This is the molar mass of the mixture. This is the number density of the mixture. And so if I can pull this out too, and I can say that N times M is going to equal rho times Avogadro's number. And so what that leaves us with is the cross-section of type J of this mixture is going to equal the sum. I've got the rho NA first. Let's do that. We've got rho times Avogadro's number times the summation across I times this mass fraction times the ratio of my microscopic cross-section to the molar mass of each individual isotope. So I got isotope here, isotope there. That's what I'm summing across. So how many ever isotopes that I have, that's what I have, number of terms I need to add up. And so we have two expressions here. The one that we derived in terms of the other. For one of the examples, we're going to actually come back to this one, even though we're not given that type of data. And the reason why we'll explain during that example. But we basically have two expressions here that we can use to calculate the overall macroscopic cross-section for the mixture as a function of all the things that I need to know about the individual isotopes that make up that mixture. So let's go to a few examples. We'll start with example 9.4. So in example 9.4, we want to find the macroscopic absorption cross-section at this energy level. And just as a reminder, this is my thermal neutron energy level. We want to find this for stainless steel. So we know the density of stainless steel, and we know that it's comprised of these four components. But stainless steel is not something that we look up in the periodic table. We can find information about all four of these, but we can't find it for stainless steel. And so we want to use the information in this table and then look up additional information that we need in order to find what that macroscopic cross-section is. So we'll use this, and our type is going to be, I'm going to put A for absorption. And we've got, I'm just going to put 304 because it's stainless steel type 304 that we're using. And with our equation, we've got density, which we know. We've got Avogadro's number, which we also know. And I'm going to sum this from I equals 1 to 4 because I have four components here. Times sigma j of I over m. So that's the main function, or the main equation that we're going to use here. So what do we know? Well, we know density, we know Avogadro's number. We're given these in the table, and we just need to go look up cross-section. We can look up cross-section, we can look up the molar mass. And so let's do this. fact, let's create ourselves, let's do this in Excel. We'll do this in an Excel spreadsheet. So let's look up for carbon, or for stainless steel, we've got carbon, we had chromium, we had nickel, and then we had iron. And we're going to look up we're going to need to know the percentage of each. Well, in this case, we need to, these are not isotopes, individual isotopes of carbon and chromium and nickel. And this is natural occurring carbon, naturally occurring chromium, naturally occurring nickel and iron and so forth. So we're going to go to this table here, and I'm going to use this previous version of the table of nuclides to go look up for carbon. This is what it tells me here. I know the percentage of C12. I know the percentage of C13. And so let's do this actually. So we have C12 and C13. I know that this one is 98.89%, and this one is going to be 1.11%. And I want to look up the absorption cross-section. So the way that we denote that is N coming in. These are neutron cross-sections. And I'm going to put G for gamma. And this is going to be units of Barn. So that we're going to look up those cross-sections. And what we want to do is find the total cross-section for carbon that is comprised of these two. And by this, what I mean is the microscopic cross-section. And so let's go look this up. C12. And my cross-section data is here. There's my total cross-section. We're looking at the radiative capture. That's my absorption cross-section. So I got 3.53 millibarns. So this is going to be 0.00353. And then I come back here and I look at the cross-section for C13. Oh, and this one I'm going to need to go somewhere else. Looks like, yeah. This usually is an error. So let's go back. We're going to have to look up this with the table here and go C13. Let's look at some cross sections. I'm going to look at the capture cross sections. Let's plot those, and then let's get the data. And then we just want to scroll down here until we see 0.0253. There it is. And this is our cross-section data, and that's in units of Barns. Barns here. Okay, and then my total then is just going to be the weighted average of the two, because this fraction, 98.89% and 1.11%, that is the number fraction, and so I can just do this and some of these. So that is my cross-section for naturally occurring carbon. That is my microscopic cross-section, my microscopic absorption cross-section for naturally occurring carbon. Now I'm just going to do the same thing for chromium and along down this list here. So we'll come back. Let's go back to the previous version. And where are we on? We're on chromium. I don't like how this is organized. There it is. So I've got naturally occurring isotopes 50, 52, 53, 54. So we're going to come back here and do 50, 52, 53, and 54. And the naturally occurring percentages here are 4.345%, 83.789%. I've got 9.501%, and then I've got 2.365%. And I'm going to go look up the cross section for each of these. My radiative capture is 15.92. Let's go back and get it for chromium 52. .764 millibarns, so that's going to be 0.764 barns. Let's go back for 3 or 53. And I could do this with any other resource too. I'm using the Korean data sets, compilation of the data sets. There's my radiative capture, that's 18.21 barns. And then finally for chromium 54. 364.4, again, millibarns, so it's 0.3644. And I'll do the same thing here. Take the product of all these and then the sum of them here. So that now is my capture cross section for naturally occurring chromium. And we'll do the same thing for nickel, the same thing for iron. Okay, the 64 there. So nickel was comprised of 58, nickel 58, 60, 61, 62, and the last one was 64, not shown on the screen. And the percentages here are 68.077, 26.223, 1.140, 3.364, and 0.926. All right, then we're going to look up the capture cross-section in units of barn for all of these. .503. So 4.503, and then this one is 2.9. It's going to be 2.509. And then this one's going to be 2.509, 2.509. And then 14.2. And the last one for nickel 64. My capture cross section is going to be 1.48. So I'll do the product here of each of these. And then my total is going to be the sum of all that. So there now is my cross-section for naturally occurring nickel. Oh, I think I mistyped this one. Let's go back and see what it is. This is 3.634. Yeah, I did type it. 634. Okay, and then we go to the last one is iron. And we've got 4 isotopes here. My isotopes are going to be 54, 56, 57, and 58. And my percentages are 5.845, 91.754, 2.119, and then 0.282. And my cross-section data. I'm just going to type this in. We can go look it up just like we did the other ones, but in order to save time, this is what it equals. And then my total again is just the sum. Okay, all of this then to find, I really missed this one, I'm doing 0.28%. 0.28%. There we go. So all of this then, these four red numbers, here, 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 and here, represent the data right here. Right, that's my cross-section data for each of the components that are in the stainless steel. So now I just need to find the molar mass for these. And once I have the molar mass, then it's just plug and chug in this equation. So what we're going to do here is then create us a table just like it was in the, just like it has in the example. So let's import our cross-section data. This is my carbon cross-section here. This is my chromium. This is my nickel. And this one is my iron. So I've got all of those. I need to find my molar mass now. And to get that, we can just go to the periodic table. We can do something similar to what we did just a minute ago, having the molar masses of each of the isotopes for carbon, carbon-12 and carbon-13, for instance. But we're going to find out that these are the numbers that are listed in the periodic table. So carbon is going to be 12.011. And chromium is going to be 51.996. The next on our list is nickel. Nickel is going to be 58.693. And then the last one is iron. And iron is going to be 55.845. So the molar mass 12.011, 51.996, 58.693, 55.845. So now we've got all the information we need. We just need the final bit that was given to us in that table was, we'll just call this FW, for the mass fraction, the weight fraction of each of these constituents. So carbon was 0.0008, 0.19, 0.1, and then 0.7092. Let me just look at those and make sure they add up to 1. They do. So there's my mass fractions of each of them, and then I just got to do this. I'm taking F times sigma divided by M for each of those. So F times sigma divided by M. And I'm actually going to convert the sigma here to units of centimeters squared. So right now it's in barns. And so this will then convert it to units of centimeters squared, because eventually I want to express the cross section in units of 1 over centimeter. And then we type in the density that was given to us in the problem statement. That's the density of stainless steel. And we can, what else do we need? I think that's it. So we go back to our equation for macroscopic cross-section. That's going to be the density multiplied by Avogadro's number, e to the 23, multiplied by the sum of all these. So I'm going to do let's do the sum here. I do each of these within the summation, add them all up, and I get a value of 0.257. And that will have units of 1 over centimeter. So that is my answer to this question. That is the macroscopic cross-section of stainless steel 304 in this case. The stainless steel that was given to us in terms of the weight percentage, the mass percentages of each of the constituents. Okay, so let's go to the final example now. In this example, we are considering a UO2 fuel pellet. So we talk often about uranium, uranium-238, uranium-235. The reality is the ceramic fuel pellets that one almost always finds in a typical BWR or PWR are made from ceramic UO2. And so it's not just uranium, it's uranium dioxide. And when we say that we are enriching the fuel pellet to such and such a percent, that's in terms of weight or mass. So this here is the enrichment percentage. Now this is high by standards of commercially available reactor fuel, but nonetheless that's what that represents. And so we're going to assume that we are enriching this fuel to 10%, which means that from a mass percentage, if I look at the UO2, there's a U in the UO2, then a certain percentage of the uranium in all the UO2 molecules is going to be comprised of U-235, and the rest of it's going to be U-238, again comprising the UO2 fuel, or the UO2 molecule. So we have to be a little bit careful with this one because we have a mixture that is UO2. But this mass percentage, this 10% in this case, is given to us in terms of the uranium, just the uranium portion of that UO2. And so we got to be a little bit careful. We can't technically use the second equation as it stands that we developed in the notes. We have to start with our original equation and then tweak it a little bit. And again, that's just because we have this mass fraction given to us that is not the mass fraction of U-235 in UO2, that's the mass fraction of U-235 in the total uranium content. But we want to know the macroscopic cross-section of the pellet, of the UO2. And this density is given to us. That's the density of the UO2. So we're going to look at molecule counts here, and then use our first equation, the first equation that we use to find the second equation in terms of mass percentage. And so we're just going to first acknowledge that because this is UO2, then the number of uranium molecules equals the number of UO2 molecules. And the number of oxygen molecules is going to be twice that of the UO2. And so I look at the number of U-235 atoms. So the number, let's call this 235. This is going to be equal to the number fraction of 235 times the number of UO2 molecules. And then we eventually want to express this in terms of weight percentages. But in order to do this, we've got to, normally we're going to have a weight of 235, and then we've got the molar mass of the mixture divided by the molar mass of the U-235. But in this case, that number here is going to be expressed not in terms of the percentage in U-230 or the UO2, but in the uranium overall. And so this will just be left as mass of uranium times the number of uranium molecules, which again is the number of UO2 molecules. And I can do the same thing for 238. 238 is going to be Fn 238 times the number of UO2 molecules equals the weight percentage of 238, which in this case is going to be 0.9, where this one highlighted is 0.1, 10%. And then this again will be mass of the uranium divided by the molar mass of uranium-238 times the total molecules of UO2. And so I'm going to use that first. We're looking at the absorption cross-section here. So the absorption cross-section for UO2 is going to equal the sum of, this is what we started with. Well, let me be consistent today. So the summation of Ni, or N, we're doing superscript for N, or for the isotope I, and this will be the absorption cross-section for each of those isotopes. So this is the fundamental equation that I would use. If I had these numbers, and this is an easy calculation, but I don't have those numbers. But I can start to relate these numbers to the other ones that I do have. And so this will be the N of 235 times the cross-section, the absorption cross-section of 235, plus N of 238 times the absorption cross-section of U238, plus the number of O16 molecules. We'll assume that the oxygen in here is exclusively oxygen 16. And so we want to look at the absorption of oxygen 16. So I can take this N35 here and substitute it there. I can take the N238 and substitute it in there. Let's go ahead and do that. And so this then is going to equal FW235 times mass of the uranium, molar mass of 235. And then I do the same thing for, I got to multiply that by the cross-section. Times the cross-section, the absorption cross-section of 235. And then I do the same thing for 238 now. I've got the mass fraction of 238 with respect to the overall uranium content, times the mass of that uranium content, or the molar mass of 238. Times the number of molecules UO2 multiplied by that cross-section, the microscopic cross-section for 238. And then I've got the number of O16 molecules. That's going to be twice the number of UO2 molecules multiplied by its absorption cross-section, the O16 absorption cross-section. So now I've got some things that I either know or can manipulate to express in terms of density, for example. So we're going to take each of the, notice each of these terms has an NuO2, so I can factor that out. The number of UO2 molecules multiplied by W235, which we have. And then we do the same thing for 238. Plus 2 times this absorption cross-section for O16. And so I want to look at the total number of molecules here, and I have density. I don't know the number of molecules, but I can express this in terms of some molar masses and Avogadro's number. So this here is going to be density multiplied by Avogadro's number divided by the molar mass of UO2. Now the molar mass of UO2 is something I can find. So what do I know? I know density is given to me. I know Avogadro's number. This is going to be 0.1. This here is going to be 0.9. I can look this up, the molar mass for U235. I can look up the cross-section data. I can look up the cross-section data for O16. So I know everything in here except for Mu and MuO2. And so once I find Mu, then I can use that to calculate MuO2. So we'll do that first. We'll find the molar mass of our uranium content. So in this case, we're going to just use the definition of what that weight percent means. So we've got F of the weight percentage is going to be Fn multiplied by the molar mass of that isotope divided by the total molar mass of the mixture. And so this mixture, this submixture, if you will, is the uranium mixture. It's got some U235, I got some 238. So I got to find the molar mass of that. Now you might be tempted to go back to the periodic table and just use that number, but I can't use that because that's a naturally occurring uranium, which is almost exclusively U238. a very small fraction of U-235. I've enriched this by a substantial amount compared to naturally occurring uranium. So I can't go to the periodic table in that sense, so I've got to calculate this the hard way. So I could now add these up. I could look at the summation over my constituents of U, in this case, of my uranium, and I would divide this Mi over there and then keep the M on this side. And if I add all those up, then I would get, on the right hand side, I would be Fn of I over M, and the M is the molar mass of this mixture, in this case uranium. We better just label this U. And so I can bring that out of my summation. And this just becomes the summation of F sub Ni, the number density of each of the fraction, the number fraction, the atom fraction of each isotope in there. And so if I take each of those and I add them together, then this thing better equal 1, right? If I take the number fraction of each of the constituents and I take those fractions, add them up, I should be equal to 1 in that case. And so eventually this here is going to be equal to 1 over the molar mass of the mixture, of the uranium mixture. And so I can use that now to find Mu. So Mu, let's see, it's 1 over Mu. I guess I better write it that way. 1 over Mu is going to be equal to this stuff here, which, though, again, this is what I know. I know the mass fractions. And so this then is going to, I've only got 2 components. I got U-235 and U-238. So this will be 0.1 over the molar mass of U-235, which I can look that up and find that it's 235.0439 plus 0.9 times the molar mass of U-238, which is 238.0508. And if I do that calculation, I find that Mu is going to be 237.75 grams per mole. So now I have that. I've got my Mu of the molar mass of uranium, but I need to then find MuO2 in order to make this complete and be able to calculate my macroscopic cross-section of the fuel pellet of the UO2. And so I am going to, this is a little bit easier, MuO2. This just then is going to be Mu plus 2 times Mo. So that's going to be 237.75 grams per mole plus molar mass of oxygen 2 times 15.995 grams per mole. And again, this is oxygen 16. This was the molar mass of my uranium mixture, which consists of a 10% mass fraction U-235 and 90% mass fraction U-238. And if I looked up uranium in the periodic table, I would get 238.03. So again, this is not that, because I've taken what would normally be the naturally occurring uranium ratio between those two, and I've enriched it, included more U-235. So if I plug this in, then I get my, I have everything here, and I'm going to plug this into my expression here. And I find that my cross-section, my absorption cross-section for UO2, and it would be interesting to also look at the fission cross-section and the other cross-sections. So that concludes this lecture. You're welcome and you're encouraged to verify your answers by going back to this expression here, and just like we did in the most recent example 9.4, go up into those tables and find your cross section. Find your absorption cross section for U235, for 238, for O16. The rest of the stuff is given to you. I know the molar mass here, I know the molar mass there, and so you're encouraged to go back and look up those values and make sure your calculations are right. You should get this value here at the end of it all. Okay, that concludes this lecture. We'll see you again for lecture 10.